Hello and welcome to this session. In this session, I'm going to talk about symbolic mathematics in MATLAB programming. So MATLAB allows you to create symbolic mathematical expressions, and this is useful when you don't want to immediately compute an answer to a problem, or when you have a mathematical formula to work on. So MATLAB allows symbolic operations in several areas, which includes calculus, linear algebra, algebraic and differential equations, the transforms such as Fourier transforms and Laplace transforms. Now, the key function in MATLAB to create a symbol is of a data is the SYMS. So when we write SYMS, then space X, this will create a symbol in the MATLAB session. This will create a symbol in MATLAB session. So when I run this one, this should show a symbol in the workspace. There will be no output, but a symbol is created. So when I run that, I should see a symbol being created with the symbol name as X. And you can see this is a 1 by 1 SYM, meaning that it's a symbol. So once we have a symbol, if I want to create another symbol, I can put a space and put Y. So this should create two symbols, X and Y. So when I run that one, I should see now the second symbol, Y, which is also a 1 by 1 SYM, meaning that it's also a symbol. Now, symbolic functions. Symbolic functions are mathematical functions that are represented symbolically rather than numerically. For example, we can write a function of x is equals to x squared minus 4x plus 3. This one is an example of a symbolic function. So in MATLAB, we shall write f of x is equals to x squared. Remember, we use the caret to type the powers. So minus 4 times x plus 3. Once this function is created, we can use it to perform various mathematical operations. So when I run this one, this should create the function f of x. So f of x is equals to x squared minus 4x plus 3. So now with that function, we can now find the value of the function at different values of x. For example, we can find the value of the function when x is equals to 5. We simply type f in brackets, then 5. So we type f, then pass in the variable, the value of the variable, which is 5. When we run, this should give us 5 squared minus 4 times 5 plus 3. That is 5 squared is 25 minus 20 plus 3. So that should give us a value of 8. So when I run, should get the value is 8. You can see now f is a 1 by 1 symbolic SYM fund. So it's a symbolic function. So the output, the function also accepts vectors and matrices as inputs. So if I write A is a vector with the elements 1, 2, and 3. These are the vector with the elements 1, 2, and 3. And B is a matrix with two rows and 2 columns. The first row with the elements 2, 3. The second row with the elements 4, 5. Then I compute f of A and f of B. So when I run this one, you see the function outputs. This is A, this is B. So f of A has the element 0, minus 1, 0. Those are the values of the function when x is 1, 2, and 3, respectively. F of B has the elements 2, 3, 4, 5. So f of B has the elements minus 1, 0, 3, 8. It's also a matrix, a 2 by 2 matrix. Now, the other thing we can do is to compute the roots of the function f of x, of the equation f of x is 0. In this case, when the function is x squared minus 4x plus 3, we can get the roots of this equation. The value such as 2 is the root of this equation. Because 2 squared is 4. Sorry, 2 is not a root. But I think 1 is a root, because 1 squared is 1 minus 4 times 1 plus 3 is 0. So for example, the value of x that will output 0 are the roots. We have seen those ones here, like 1 and 3, because the output here was 0 and 0. So we can find the roots by using the function solve. Then we pass in the function f. We use the MATLAB function solve. Then we pass in our function f. So we write the roots is equals to. So we pass in the function there. When I run this one, I should get the roots of the equation. Sorry, I did not learn that one. I should get the roots of the equation x squared plus minus 4x plus 3. The roots are 1 and 3. We can also compute the derivative of the function. The derivative of the function is obtained using the diff function, diff. Then we pass in the function there. So the syntax is diff, then we have the function, the variable, and n, where n is the order of the derivative. So for example, we want to differentiate the function f with respect to x, and we want to find the first derivative. So n will be 1, the variable will be x. Then here we shall just write f. So for example, we may write sym xy, that creates two variables x and y. Then we define the function fx, y. This will give a function of two variables, x and y. So let me write that section. So we have the function of two variables here. So if we want to find the derivative of f with respect to x, then we write diff f, we want to differentiate with respect to x, and then we indicate 1, we want the first derivative. If we want to differentiate with respect to y, dfy, we write diff f, the variable is y, then we say it's the first derivative. We run that, we should get the first order partial derivatives. The first one with respect to x, and the second one is a derivative with respect to y. The first one is the first order partial derivative of f with respect to x. The second one is the first order partial derivative of f with respect to y. So if we wanted the second order partial derivatives, we would just change from here to, from 1 to 2, here and here. So for example, if we write diff f, x, 2, means that we find the second order partial derivative of f with respect to x. This can also be achieved by, instead of writing 2 here, we can indicate that we want to differentiate with respect to x first, and then again with respect to x. So we write diff, then f, x, x, meaning that we differentiate first with respect to x, and then again with respect to x. So whether we write this one, 2 here, or we write x, x, we should get the same result. So when I run, that should give me the second order partial derivative of f with respect to x. Second order partial derivative of f with respect to x. You can see both give me the same thing. So similarly, if I want the second order partial derivative of f with respect to y, I'll write diff f, y, 2, or f, y, y. should give me the second order partial derivative of f with respect to y. So if I want the mixed derivative now, if the derivative with respect to y, to x, then y. So I will write the diff, then f. I'm differentiating the function f with respect to x first, then with respect to y. This should give us the mixed order derivative. So if I want I learned that section, should get that derivative. If I want the third order derivative with respect to x, then y, then x again, I'll write diff, then f, then this one means that I differentiate first with respect to x, then y, then x. So with this, I can go to any order that I want. Can differentiate to any order. So we have integration. Integration can be achieved using the function int, then you turn in, you pass in your function there. So for example, with the indefinite integral, we write, for example, f of x is equals to x cubed minus 5. If I run that section, I have f of x is equals to x cubed minus 5. Then the integral of f will be int. Then I pass in this function. I should get x power 4 over 4 minus 5x. But now when I run this one, it may not be formatted the way I want. You see, this one is x multiplying x cubed minus 20 divided by 4. But if you open the brackets, you see that this will be x power 4 minus 20x. And then when you divide both terms by 4, you get x power 4 over 4 minus 20x over 4, which is just the same as 5x. But instead of doing that, we can use the function expand, then pass in our integral. So expand, then pass in our integral. This should just give us the integral in the expanded form. Sorry, let me run this other section. So x power 4 over 4 minus 5x. That's the way I would have wanted our integral to be. We have a definite integral. If we have the limits of integration, we simply have the same function int, but we pass in the other two arguments, which are the lower and the upper limits. For example, if we want to compute the integral from 1 to 5 of f of x, we write int f1, 5. Definite integral here will be int f. We want to integrate the function f with the lower limit as 1, and the upper limit is 5. Working out that will give us the value as 136. If I run that one, I'll get the value as 136. We have what we call the anonymous function. Anonymous function. An anonymous function is a function that is not stored in the program file, but is associated with a variable whose data type is a function header. Anonymous functions can accept multiple inputs and return one output. They can contain only a single executable statement. For example, we can write the cube root. If we want to find the cube root, we can create a program called croot, or a function called croot. It's equals to, we use the function header, which is at, the at symbol. Then we pass in the variable, which in this case we can say, we may want to say the variable is x. And let me clear the variables first. So clear the workspace so that we just see clearly what this will mean. So C root is equals to R. When we pass in the variable, the variable there, which is x, then we write x dot, then caret. This is the power of 1 over 3. So C root is a function handle. The operator at creates a handle, while the parenthesis occurring immediately after the operator at includes the function input argument. So this anonymous function will take a single input. This particular one should take a single input and output the cube root of that. We call this function by supplying the input. For example, we write a is equals to c root 27. This should give a cube root of 27. So when I run that, I get the value of 3, which is the cube root of 27. So we can have this. We can create the symbolic function also using the function handle. For example, SYMSX, this creates a symbol in the MATLAB session. Then G is equals to the handle at, then we pass in the variable x cubed plus 4x minus 5. Then this G is a function handle. Then now we write y of x is equals to g of x. So y of x will be a symbolic function. So we can create a symbolic function y of x by simply using the function handle. So this creates a function handle g and a symbolic function y. Some points to note: an anonymous function can accept any number of inputs and return any number of outputs. It can be defined in a MATLAB command line, script, or even function. The syntax is f is equals to the handle, then we have the argument list. You can have one argument or even more, then the expression. For example, we can write power r is equals to at x comma n, then x dot our n. So this function will accept two arguments, x and n, and compute x power n. So you call this function by providing the inputs in the command we do. So for example, when you run this should create a function handle. Let me clear the workspace first, then run again. So we have that. Then now if I write power 2 comma 3, this should compute 2 to the power 3, which is 8. So if I write another example, f is equals to at x, y, z, this is a function with 3 variables. And the expression is x times y times z. This should give basically a product of the 3 inputs. So when I call this function will accept 3 inputs and to produce the output, which is the product of the 3. So when I run this f235, I should get 2 times 3 times 5, which is 30. So it is important to note that an anonymous function accepts inputs which are themselves symbolic variables. So for example, here, with the function f here, it can accept inputs which are symbolic variables. So if I have the symbol t, then I call f with the variables t, 2 times t, and 1 minus t, then I'll get an output which is the product also of those 2t squared multiplying t minus 1, negative of that. So using the dot operator when defining the anonymous function creates a function which can accept a vector as input. So it is important when we are creating an anonymous function, we use a dot operator, so that even if we want to get an input, to use an input as a vector, the function will accept. So next I'll talk about displaying the output in MATLAB. There are several ways to display the output data in MATLAB. The simplest way is just to leave the semicolon off at the end of the statement, and it will be printed in the console. For example, when we write 2 plus 3 and learn, we get 5. Now, we now explore the few other ways to display the data. One is changing the default format. We have seen that in all the outputs we are getting the output correct 4 decimal places. So we may want to change that. So when data is echoed in the command window or console, integer values are always displayed as integers, character values are displayed as strings, and other values are printed using the default format. And the default format shows the 4 digits after the decimal. And it may be displayed in a scientific notation with the exponent if the number is too large or too small. For example, when we type x is equals to 100.11, y is equals to 1001.1, and z is equals to that, and learn, then the output is generated as what we have here. This output, which is the default format. We may want to change the default format. So the format command changes the default format according to the values given in the table below. So the format short will give the 4 digits after the decimal. Format long will give 14 digits after the decimal. Format short E outputs 5 digits plus the exponent. Format short G outputs 5 total digits with or without exponent. Then there is the format long E, the format long G. There is the format bank, which gives the currency format. There is the format lat, which gives the rational numbers. There is the compact, which suppress an extra line feed, and loose, which restores the extra line feed in the command window. So these are some of the commands that you can use. For example, we can write A is equals to 6 divided by 7. That should output 0.8571. That's the default format. But if we type format long, then output A should give 14 digits after the decimal. Format lat should output a rational number, a fraction, 6/7. So the default format for MATLAB is usually the format short, which prints the results correct 4 decimal places. So if I type format short and then I output A, this should give me 4 decimal places. We have the disp function. So another way to display data is with the disp function. The disp function accepts an array argument and display the value of the array in the command window. If the array is of the type character, then the character string contained in the array is printed out. This function is often combined with the functions num to string to convert a number to string, and int to string to convert an integer to string, and this creates a message to be displayed in the command window. For example, the following MATLAB statement will display the value of pi is equals to 3.1416. The first statement creates the array containing the message, and the second statement displays the message. So if we write string equals the value of pi equals num to string, this one converts the pi to a string for the purposes of the display. So when we run this one, it prints the value of pi is 3.1416. The other formatting is to use the fprintf function. A more flexible way to display data is with the fprintf function. The fprintf displays one or more values together with related text and lets the programmer control the way in which the displayed value appears. So the general format is fprintf format, then data, where the format is the string describing the way data is to be printed. So for example, we write fprintf, see that we use the quotation marks. The value of pi is then %f. Now, when the percent here is the placeholder, then f indicates that the output is a floating point decimal. It's a float. Then there is an extra character here, which is a next escape character, \n, meaning that we put a line feed after printing this result. So this should output the value of pi is 3 point. This will print the value of pi correct to 5 decimal places. So this will print the value of pi is this, followed by a line feed. So the character %f are called the conversion character. These are basically the placeholder. The % is basically the placeholder, while \n is an escape character. Indicate a line feed should be issued so that the following text, the text that follows, should start on a new line. There are many types of conversion characters and exit characters that may be used with the fprintf function, and the table below just summarizes that. We have %s, this one is for a string, %c to display the character, %d to displace an integer, %f displays values as floating point numbers. If we write %.2f, this will display the number correct to 2 decimal places. \n is the line feed, \t is the tab space. Double backslash will print a backslash, and the double % will print a %sign. For example, suppose we type the following: name is equals to Dan Onyango, age is equals to 28. Then fprintf, my name is %s. This one indicates that the input here will be a string. \n, this will create a new line, a line feed. I am %d, this one will print an integer here. D is for the integer, years old. So there will be a first line which we will expect my name is, then the name. Then the second line, I am dash years old, then the number of years here is name and age. So the name here is Dan Onyango, which will be printed here. And the age, which is 28, will be printed here. So the output should be, my name is Dan Onyango. Then a second line will be, I am 28 years old. So when I run this one, I should get my name is Dan Onyango. I'm 28 years old. Note that the fprintf function has one very significant limitation, that it displays only the real portion of a complex value. It is very important to note this because if the output expected is a complex number, then fprintf will yield a long result. If you write the root of a given equation is %f, then the input here is 2 plus 3i. Fprintf function will ignore the 3i part and only output 2. The root of the given equation is 2. So the imaginary part is lost. So if you are expecting to get some imaginary numbers in your solution, then it is important to use the disp function. We have the input function. The input functions are used to prompt the user for input during the execution of a script or function, and it allows for dynamic interaction with the user and facilitates the creation of more flexible and interactive program. The basic syntax is response is equals to input. Then brackets we have prompt for the user. Here, you just type anything that you want the user to do. Then you can put comma s if you expect the user to enter as a string. For example, if you are expecting that what is to be entered is a name, for example, which is a string, then you put s. But if you are expecting a numeric value, you can leave this part out. So in this case, for example, name is equals to input, enter your name, then s, then display hello name. So when you enter the name here, like James, the output should be hello James. So when I run this one, I want to run this one and enter the name in the command window. You see, the prompt will come in the command window, and I want to enter the prompt, the name as James. So I'll type James and then press enter. So when I go back here, so I think this one has, let me run again. So it has, the output now is hello James. I want to put the name again, James Maina, and go back to my code. Hello James Maina. Let me break this code into two parts so that we run each part separately. I put a section break, then run this one. So I'll type here James Minor. Then when I run the second part, now this one, I get hello James Mine. So some points to note here. Some key points to note. Prompting for input. The primary purpose of input is to display the prompt and wait for the user to enter the input. So when you run, you get the codes waiting for the user to put the input. You put the input there. So the input basically prompts the user to enter something. Then you press enter. After that, now the next line of code can run. Then we have the data specification. The second argument to the input specifies the data type that of the input. It can be omitted for numeric input, but it is useful for other types of strings. So here, if the input expected here was numeric, like for example, if you are prompting the user to enter their age, you don't have to specify the second argument. Here you can omit that. You can omit the whole of this. But if you are expecting a string, then you need to enter that. So if the second argument is omitted or not provided, the input assumes that the input is to be numeric. For example, age is equals to enter your age. If I run this one, then I'll be prompted to enter the age. Maybe the age of that person is 28 or 38. So in this case, the variable age here has a value 38. So the string input, to obtain the string input, the second argument should be specified as s. For example, that. So expressions evaluation input can evaluate MATLAB expression entered by the user. So for example, results equals enter a mathematical expression. So you can enter a mathematical expression. For example, something like this, interactive program to calculate the area of a circle, the radius. Radius is equals to enter the radius of a circle. If I run this one, if I run this, and then enter the radius, I'll be prompted to enter the radius of the circle, and then enter the radius as 7. So what happens? The area, the program computes the area as pi times the radius squared, which is the area of a circle, and then displays the area. The area of a circle is numbers to string area, which is 153.938. If I run again and enter a different value, now like 14, I'll get the area of the circle of radius 14, which is 615.7522. So in this example, the user is prompted to enter the radius of the circle, and the program computes and displays the area. The code includes basic form of the error handling to ensure the user enters a numeric value. So basically, we can use the input function to create a more interactive programs that prompts the user to enter some values for the calculation. For example, like the one we have seen here, we can create a program that prompts the user to enter the radius of the circle, and then the program computes the area. So in this case, by running this, the user can be able to compute the radius of different circles without having to modify the code. So that is the advantage of using the input function. So for this one, I'll stop at that, and then the next one I'll look at the flow of control to create a program that makes decisions based on the input. So thank you for listening to this, and we shall meet in the next one.